there's a composite function theorem. So I kind of want to unpack this for you a little bit. When I see this word composite function, that's the same thing as a composition of two functions. Okay, composite means composition. So this is like a function inside of a function. So let me explain what the thing is saying first, and then I'll draw a picture to help you understand it. So that missing block, or that missing space there, is if f is continuous at L, and the limit as x goes to a of g of x is equal to L, then f of g of x is continuous at x equal to a. So that's the actual theorem, but I want to help you unpack it. Okay, so the way that you want to think about this is you have your x value. First, you plug it into the g function, and I'm thinking of the function as like a machine here. So it's like this is g, and then what comes out is your g of x, right? And then you take that guy and you plug it into your f function. And then the output of that is f of g of x. This is what we call a composition of two functions. Marina, I did 1, 5, 6, and 7 already. I did 6, 5. The answer to your question is yes, I did all of those. Some of them I did last class. Today I only did 6 and 7. So it's all available on video. Oh my God, am I recording this? Oh yes, phew. So we're good, okay. So like, what is this guy saying? What is this theorem saying? This theorem, we know that this function is continuous. First of all, what's basically happening is we're taking an x over here, and we're trying to see what happens as we get close to a, right? So it's almost like, okay, we're taking an a, and like we're plugging it in right here, and then the output of this guy, where does it look like it's going? It looks like it's going to L. And then you take that result and you plug it into F, but you already know F is continuous at L. So it's already continuous at this input value. So what this theorem is saying is, well, if you know this part is continuous and the limit of this part is equal to L, then if you looked at the composite function, that is, you first did G, plug the result of that into F, that composite is continuous. So that's all this is saying. Okay. All right. So I'm gonna show you how to evaluate this limit right here. Okay. Yeah, this limit, this example 10 is going to involve this composite function theorem. So when I look at this, if I want to calculate this limit, we know that sine is continuous on its domain. And so in particular, f of x is continuous at L because sine is continuous everywhere. Okay, so it's like our f of x is equal to sine of x. It's continuous everywhere. You guys know sine looks like this. Domain knows all real numbers. The range is from -1 to 1. Our g of x is just going to be this inside function, x minus pi over 2. That's the inside function. We can rewrite this limit as the sine of the limit as x goes to pi over 2 of x minus pi over 2. And when I look at the limit of the inside, this is just a line. The slope is 1. The y-intercept is negative pi over 2. This is a continuous function. So I can plug in the pi over 2 in there. So that's going to give me sine of 0. And I know what sine of 0 is. Sine of 0 is just 0. So this limit is equal to 0. So this composite function theorem is basically saying, oh, when you know the outside is continuous, move the limit inside. Calculate the limit of the inside first and see what you get. I guess I should also say that the limit as x goes to a of f of g of x is going to be equal to f times the limit as x goes to a of g of x. That's what I really did here, and move the limit inside. And we actually know what this guy is. That's equal to L. So this is just equal to f of L. And in our case, our L was 0. So it's f of L. Okay. What's an L there? Yeah. All right.